So next, let's take a look at a topic called differentials. Okay, um, and here's sort of the idea, right? You know, say say we want a bit more information than the derivative will, offer us, right? Rather than looking at the rate of change, what if we wanted to estimate the actual change, right? Not the speed at which it's changing, but how much it does indeed change. Say you want to look at what happens to profit after a small nudge in price, right? Sort of like what we were talking about a little bit on Tuesday, right? Or if you increase, say you're a biologist, right, and you're studying some bacteria, right? You want to be able to know if you increase the amount of bactericide, how much will that affect the population of bacteria? Not the rate of change of these quantities, but the actual physical change. Okay, and this is where something called a differential uh, gets, really useful. Okay, and here's what I want to introduce you to, right? Um, there's this notation delta x, right? Um, and simply delta x is x2 minus x1, right? It's some finite change in x, right? As opposed to like little dx, right? Which is the behavior as this change becomes small, right? Some finite step in x, right? And so if x2 equaled 3.2 and x1 equaled 3, then delta x would be 0.2, right? It's the size of some step, right? Um, Notice this is sort of the same role that our h was playing when we were defining our derivative, right? And it's like, okay, we have this idea of delta x. Can we define delta y if y is a function of x? Well, sure, right? Because this is just sort of the same idea of what we were talking about when we were, developing the derivative. Delta y is going to be f of x plus delta x minus f of x, right? Sort of looking at a picture of this, let's get some generic graph. Say that guy, right? We'll choose some point, call it x, right? Some finite step here to x plus delta x, right? This is going to have some function value f of x, right? And then right here is going to be f of x plus delta x, right? Sort of putting a little bit more information here, right? We have this, this, and this, right? This again, this quantity here is delta x, and this quantity here is delta y, okay? And in practice, if you're trying to calculate delta y, it's a little bit cumbersome, right? Like say f of x equals x cubed, right? If you're looking at, say you start at x equals 2, right? And you have a delta x of 0.1, right? Well, then your delta y is going to be 0.120601, right? It's this, annoyingly difficult value to calculate because you need to end up doing 2.01 cubed, right? Which is, is it difficult? No, not necessarily. Is it tedious? Yes, absolutely, right? That's one of the things that I want to make a distinction of, right? Calculating delta y by hand, it's not difficult by any means, but it is tedious. But here's what we can do, right? Just as we used these tangent lines to approximate for our marginal cost functions, notice something here, right? What happens if I drop a tangent line? Well, this quantity here, that's pretty close to delta y. Is it going to give me exactly delta y? No. But it is going to get pretty close. Notice that, and this kind of goes back to what I had mentioned back near the start of the quarter, right? Differential calculus is the study of functions who think that they're lines, right? Because notice, if I zoom in enough, this red function starts to look an awful lot like a line. As I get closer and closer and closer, it looks even more like a line. So if I just let this function think it's a line, well, at this point, right, the line that it thinks it is this tangent line. So that means that if delta x is small, this value here, right, which we'll call dy, this value dy is going to be a dang good approximation of delta x, or of delta y, right? And notice that dy over delta x, that's going to be the slope, right? That's our derivative at x. I know that this is a little bit, weird and complicated, and I promise it'll make more sense once we start doing problems. But like, do bear with me here, right? This means, right, that since I know that dy over delta x is my derivative at x, okay? This is not some weird, like dy dx thing. This is a physical fraction, right? That means that dy is the derivative times delta x. But as we saw by the picture, this approximates delta y. So what that means is, right, if I want to calculate delta y without going through, cubing 2.01, right, I can just calculate this. And that's a little bit, or rather, in most cases, that's a lot simpler. Okay, let's sort of clean this up and sort of write down these ideas, right? So we'll say y equals f of x, be a differentiable function. Okay. Well then what, right? The differential dx, right? Where again, x is our independent variable. The independent variable x, well, it's what? It's dx equals delta x, okay? Things get, more complicated when we start to look at our independent variable. So the differential dy of the, dependent, right? Dependent again because it depends on x. So we'll write that a little bit cleaner. Dependent variable y is dy is f prime of x delta x, right, which since delta x and dx are the same, we can also write this as f prime of x dx, okay? Here's what I want to draw your attention to here again, right? For our independent variable, there's no difference between delta x and dx, right? Both measure the change in x from x to x plus delta x, right? For the dependent variable, right, delta y measures the actual change, right? As x changes from x to x plus delta x. Whereas our differential dy, it approximates the change, right? It approximates the change, but it approximates the change very, very well, as we'll see when we do some calculations. But it's also way easier to calculate, okay? So let's sort of look at that example that I talked about, right? Let's say let y equals x cubed, right? What's our differential, right? Our differential is the derivative times dx, right? So it's going to be 3x squared dx, okay? For this next part, right, we can say what is dy if x changes, say, from 2 to 2.01, right? In this case, we can see dx equals 0.01, right? So that means that dy is 3 times 2 squared times 0.01. Right? And this is, it's a little bit tedious to do by hand, right? When you work it out, you get 0.12. But compare that, right, to actually trying to calculate delta y here, right? Delta y here involves doing this. And sure, multiplying this by that is a little bit annoying, but cubing something like this is way more tedious, right? But then look at this, right? When we actually physically run this math, we get this 0.120601. This is a dang good approximation. The difference between these two numbers is 0.3 zeros before you even get a number, right? This is a really good approximation. So the moment that we need to approximate this gets a lot simpler, right? Or how about this, right? Maybe you're trying to approximate the square root of 26.5, right? For whatever reason, you need to do this. But here's what I want you to notice, right? 26.5 is pretty close to 25. So here's what we can do, right? We can say set x equal to 25 and delta x equal to 1.5, right? That means that the square root of 26.5 minus the square root of 25, which we know, right, that's equal to delta y, okay? So that means the square root of 26.5 is delta 5, or delta x, or delta y, sorry, plus 5. Now, difficult to calculate delta y here, right? but pretty easy to calculate dy, right? Because what's dy? Right? Because again, this is approximately equal to dy. Well, dy here, right, is going to be f prime of x times dx. Well, our derivative, right, is 1 over 2 root x. We're multiplying this by dx, right? But if we plug in x equals 25 and then say dx equals 1.5, right? Again, where this vertical bar tells us to evaluate it at these points. Well, that means that dy is going to be 1 over 10 times 1.5, right? Which is 0.15. So then we get that the square root of 26.5 is approximately 5.15. Now, if you go to your calculator and you plug this in, you're going to see that it's 5.14782. Okay, so the error here, once again, is fairly small, right? This gives us good approximations. Okay, but we can use this, for other types of estimating as well, right? Say you're going on a road trip, right? And whether you're going on a road trip or you're running some shipping company, right? Say you're going on a road trip, right? Some really long road trip, and the cost incurred, right? Through model building or whatever, that the cost incurred relative to your average speed, right, is something like C of V, the 125 startup plus your speed plus 4,500 divided by V, right? And then say you want to approximate the change in your total operating cost, right, when you increase speed from 55 to 58 miles an hour. And you might ask me the question, why do you want to do that, right? Like, why would that, lead you to, what situation in the real world would you actually run up against a model like this? And I do think that that's a fair critique of these sorts of questions, right? If you're running the road trip, right, then you're almost never going to actually see a function like this. But you are going to be doing estimating like this in your head, right? Often the fuel efficiency changes when you increase speed, which is going to change when you have to fill up gas, right? If you're, running a shipping company, sure, these sorts of problems are going to be baked into a computer, but what happens when you need to make a decision on the fly, right? And that's sort of what I mean when I talk about that calculus is like weight training for your brain, right? What it's doing is it's getting you used to thinking about these sorts of things. That way, when you come across these problems in real life, in your businesses, in your personal life, yeah, sure, you're not going to see a function like this, but you will definitely see these sorts of ideas of like, what are the trade-offs? How can we approximate, right? And the background in calculus and the weird exercises that we're doing by looking at how the volume changes, compared to the speed that the radius changes in a perfectly spherical balloon, that sort of practicing, looking for those shifts in perspective. Okay. And I sort of go on that tangent because I do understand that asking a question like this, right? This is example 5 from section 3.7 in the textbook. It is kind of ridiculous because you're never actually going to see that, right? And with the test coming up on Wednesday, I think those, there's a decent chance at least that those worries are in your mind. Like, why does this matter? Yeah, we had 45 minutes or whatever on Monday looking at these marginal cost functions, but like, why do these questions matter? And like I said, it's training you to get used to these ideas, right? And I'll be sending out an email at some point today with sort of more information on the exam, and how I think about grading. But the thing that I'm interested in seeing you doing is actually using your brain for these, right? Not looking for some formula, and like trying to find the right numbers to plug in. I'm interested that you can sort of solve these problems with care and with careful reasoning, right? And consider what you're doing rather than blindly following ahead. Hopefully that's a bit of a consolation. Maybe it is, maybe it isn't. Um, I'm always reachable via email, and you can always drop by my office hours, if you have questions about sort of how to think that way. Um, but that tangent aside, let's jump into this example, um, which I believe will be our last example for this sets of lectures. We'll make it a little bit shorter since the last two lectures have been on the longer side, right? So if we want to approximate the change from v equals, say, 55 to v equals 58, again, here's kind of how we want to think about doing that, right? We can set delta v, or dv, whichever you prefer. In this instance, they're equal, right, to 3. And then delta y, which is the actual change, is approximately equal to dy, which is then equal to the derivative of this, right, which is going to be the derivative of 125 is 0, plus 1 minus 4,500 over v squared, and that's multiplied by 3, right? And in particular, right, we need to plug this in for v equals 55, right? Because our delta v is dependent on our specific value of v. So that's going to come out to 1 minus 4,500 over 3025 times 3, right? And if you were to evaluate this expression, via whatever is your favorite means, via calculator or by hand or whatever, you're going to come out with that this is approximately, right, because we're going to need to do some rounding, negative $1.46, which means if you speed up 3 miles an hour, you're going to save about $1.50 on your total operating cost. And you'll get there sooner. So, depending on what the speed limit is, right, all signs would point to 58 miles an hour here. Okay. It's going to wrap it up for this lecture. I won't see you on Tuesday, right, because there won't be any lectures then. Again, if you have questions or concerns about the content, drop by office hours, shoot me an email. I'm here, as the person teaching this course to be a resource for you as we go through this material. And so that's going to wrap it up then. If I don't see you in office hours, the next lecture will be going up a week from today after the exam. See you then.